While we consider stars, we likely envision minimal, clean things in the evening sky. Fundamentally, this is the image by which we see them from down here on the planet. In any case, stars like Betelgeuse are something else entirely. Sincerely, one of the most important stars, Betelgeuse happens to be a lot more noteworthy than our Sun. For a genuinely extended period of time, this star has surprised experts. Yet, as a matter of fact, something extra disturbing has been occurring with Betelgeuse, making experts and other well-informed people extremely concerned. Oblige us in this video as we analyze the profound news about Betelgeuse, its impending annihilation as expected by the James Webb Space Telescope, and how this new headway will influence our universe and our lives here on Earth. As made sense of by physicist Michio Kaku, Betelgeuse is an endless miracle, a colossal star that has captivated cosmologists for such a long time. A Greek space master named Tony was quick to think that it is this star. It is gigantic to the point that it tends to be found in the evening sky from Earth, especially during winter. Assuming you're into stargazing, you've likely seen or heard about this star. It is the orange-red star that marks the upper left shoulder of the Orion constellation. So, you see, this star is old and still remains one of the brightest stars in the night sky. One thing about Betelgeuse's quality is that it doesn't remain consistent. Perhaps it shifts. This variance is one of the charming properties of the star, yet it isn't the only one we ought to check out. Some of Betelgeuse's particular properties are unique. The vast majority of the stars you find around evening time are quite far from Earth. The closest star is 4.2 light-years from Earth. In the event that you don't know how the term light-year connects to distance, picture it like this. Consider moving at the speed of light for an entire year. It's been proven that light can cover a distance of 186,000 miles per second. Consequently, the distance light can cover in a year is practically equivalent to 1 light year. Assuming that you figure it out, you'll have billions of miles. So, when we say the closest star is 4.2 light years away, it implies it is billions of miles from Earth. At any rate, a couple of stars are a lot farther, and Betelgeuse is one of them. Betelgeuse is around 600 light-years from Earth. So if you somehow end up traveling to it at the speed of light, it would still take 600 years. We can't move that quickly, not even with our fastest spacecraft. However, this star can still shine brightly in our sky. If you're wondering how Betelgeuse can be so bright despite its distance, it's because of its phenomenal traits like size and brilliance. Betelgeuse is almost several times more massive than our Sun, and its reach is believed to be significantly greater than that of the Sun. Tragically, it appears as a disk in space when utilizing complex telescopes, while other stars appear as tiny points of light. This appearance is believed to be an effect of the reactions in the outer layers of its atmosphere. In terms of mass, Betelgeuse measures around 12 to 19 solar masses. A solar mass is the standard unit of mass used by astronomers, where 1 solar mass is equivalent to 2 times 10 superscript 3 kilograms. Researchers can't determine the exact mass of Betelgeuse since there are no other planetary bodies orbiting it for comparison, and obviously, we can't measure it directly from here. The fact that this star is between 12 and 20 times heavier than our Sun makes it dazzling. The brightness of Betelgeuse ranges from +0 to +1.6 in apparent magnitude. In more common terms, Betelgeuse is several times brighter than our Sun. No wonder it was nicknamed a red giant. Anyway, the brightness of Betelgeuse doesn't remain consistent. It fluctuates. This change in brightness is due to its pulsations. Generally, Betelgeuse expands and contracts. When it expands, it becomes brighter. When it contracts, it darkens. This interaction can last from 10 to 100 days, or even longer. One intriguing property of Betelgeuse is that its surface is covered in dark magnetic spots. The magnetic field here is far stronger than on the Sun's surface. However, the downside is that these strong magnetic spots restrict the flow of hot gas to the star's outer surface, making the star cooler in these regions. The fact that Betelgeuse has a lot more of these spots compared to our Sun explains why it is cooler than the Sun, despite its size and brilliance. The Sun also has dark magnetic spots, but those on Betelgeuse are much larger, and the differences are striking. To give you an idea, the spots on Betelgeuse can be twice as large as Earth. Betelgeuse also boasts a magnetic field that is several times stronger than that of the Sun. This field is why, when seen through a telescope, the gases on the surface of Betelgeuse appear to be in twists or curves. Betelgeuse has a surface temperature of around 3,500 Kelvin. This low temperature contributes to the low energy produced by the star and its faint red color. Betelgeuse is a red star, but it wasn't always red. It was yellowish around 10,000 years ago, similar to our Sun. Over the years, its color started to shift to orange-red, and then around a few years ago, it slowly began changing into the red star we know today. This fact has led researchers to believe the universe is evolving. However, this isn't the only perspective presented in the field of cosmology. Besides the theory of the universe's origin, in 1955, for example, an article appeared in NASA Spacetimes arguing that there could never have been a Big Bang since the universe has existed for an infinite time frame. In this view, the expansion of the universe would be non-existent, and the constant arrangement of matter could provide the appearance of steady development. Moreover, another spellbinding speculation rises out of the domain of quantum materials science and string hypothesis. Some tests have proposed that our universe and all that is in it may basically be a flat, 3D picture projected onto a surface. Hence, it is conceivable that our world is a consequence of a higher layered reproduction. While this may seem like the plot of a complicated science fiction film, it could indeed be associated with the Kesef scale, which measures the degree of advancement of a progress in light of its capacity to harness energy. On the off chance that there were a Type 3 civilization able to completely harness the energy of a whole universe, it could have made an ideal reproduction, making reality itself a muddled matter. Investigating the profundities of cosmology and the starting points of our universe leads us into a space of significant mystery and progressing logical request. The new pictures captured by the James Webb Space Telescope have reignited conversations about the actual texture of our reality, testing laid-out hypotheses and inciting analysts to re-examine fundamental components of cosmological understanding. At the core of this request lies the hypothesis of how things came to be, a supporting of current cosmology. As indicated by this hypothesis, around 13.8 billion years ago, the universe rose from a phenomenally thick and hot state, growing quickly and resulting in space, time, and matter as we understand it today. This tremendous occasion isn't simply an impact within earlier space. Maybe it could incorporate the very start of room itself. The possibility of a peculiarity, where gravitational powers are intense to such an extent that space and time become endless, supports how we may comprehend this early-stage epoch. However, the disclosure of early galaxies by the James Webb Telescope challenges our presumptions about how rapidly structures formed in the universe's earliest stages. These galaxies, identified within a couple 100 million years of the Big Bang, appear shockingly advanced and massive, challenging presumptions based on current cosmological models. One of the major questions raised by these discoveries is the concept of fast expansion. According to the common hypothesis, expansion happened within parts of a second after the Big Bang, causing the universe to develop decisively. This rapid expansion would explain the consistency of the cosmic microwave background radiation observed across the universe today. However, the new revelations suggest complexities in the early universe's advancement that might require adjustments to inflationary models. The improvement of galaxies, like those seen by the Webb telescope, prompts cosmologists to rethink the timing and processes governing the universe's early advancement. These galaxies, now significant in size and mass, suggest a density of matter that surpasses past gauges. The mystery develops when taking into account how such massive structures could form and evolve in such a relatively brief time frame. Additionally, the discovery of these early systems raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework fundamental for galaxy development, the distribution and properties of dark matter in the early universe remain questionable. Considering these astrophysical mysteries, theoretical physicists are investigating alternative cosmological models that challenge the conventional Big Bang view. Some theories propose that our universe is merely one among many in a vast multiverse, each with its own unique physical laws and constants. These ideas, rising from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously envisioned. One hypothesis gaining traction is eternal expansion, in which universes constantly arise from a larger, expanding space. This theory holds that our universe could be just one bubble among countless others, each with its own distinct properties. The challenge lies in finding another provocative hypothesis, that our universe exists within a simulated reality, similar to a computer-generated game. This thought aligns with advancements in artificial intelligence and computational science, where simulations can reproduce complex systems with remarkable fidelity. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising significant philosophical and scientific questions about the nature of existence. As observational cosmology continues to uncover the universe's vastness and intricacy, telescopes like the James Webb Space Telescope, with their striking responsiveness and resolution, promise to unveil even more mysteries of the universe. Future observations might shed light on the earliest moments of the universe, offering insights into its ultimate fate and the fundamental rules governing its advancement. Beyond observational cosmology, particle physicists are exploring the crucial particles that shape the universe. The mission to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central objective of theoretical physics. Ideas like quantum gravity and string theory offer potential frameworks for understanding these fundamental interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself remains a subject of intense debate. Time, as we experience it, flows from past to future. Yet quantum theories challenge this idea, proposing that time might be nonlinear or even discrete at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our perspective on the universe's origins and development. Additionally, the quest for extraterrestrial life continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet environments, will further illuminate this exciting field of research.